Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. In this lecture, we'll be talking about cyanohydrin formation. And how do we get such a molecule? If you start with a carbonyl and you add a cyanide group to it in the presence of trace of acid, we can get a molecule that it has a CN functional group plus hydroxide at the same time, and that's going to be a cyanohydrin molecule. Reaction is going to go through a nucleophilic addition, nucleophilic technically attack to the carbonyl group, and because carbonyl it has a positive charge. Very soon it will be, it will be looking for negative charge or lone pair in any nucleophile, and the nucleophile will find it. And now we'll have oxygen with a 3 lone pair. That oxygen is not going to be stable. If there is any source of acidic H inside the solution, very soon it will be neutralized by taking H from that acid or that acidic, technically H, and it will give us an alcohol plus a cyanide attached to the cyanide group attached to a carbon. Now, as you see, we started from a carbon with sp2 hybridization. Now we have a carbon with sp3 hybridization. That means we have a chance to get a chiral center. It depends what we start with. In this case, because we have 2 identical methyl substituent, and that carbon, the central carbon, is not going to be a chiral center. But the question that I want to actually ask, or maybe you already asked yourself about it, why should I care about cyanide? It's just a normal nucleophile that got added to carbonyl. What's the point of learning technically chemical reaction of cyanide with carbonyl? Let's see how we got actually to cyanohydrin. We started with a carbonyl, and we have a carbon with sp2 hybridization. That means we have a sigma and pi bond. And why did we get nucleophilic addition technically reaction? Reason behind it was because there was a pi bond, and we managed to take the pi bond to a sigma, and that one is going to give you a negative delta H. So that means that's a favored process. Okay, now I got cyanide, and what's the point of having cyanide? Let's zoom on cyanide. So I'm going to zoom on this substituent. What do we have there? We have carbon attached to nitrogen. Nitrogen is attached to carbon through triple bond. One of them is sigma, but it still has 2 pi, 2 pi technically bonds. Okay, and so not only I added a new carbon to the system, and I managed to decrease the number of carbons. Okay, I added a heteroatom, which is nitrogen. And the third thing is, when I added carbon and nitrogen, still I kept a pi bond inside the system, and that's going to give me a chance to manipulate that triple bond. Because anytime you have a pi bond, you can do nucleophilic addition, like what we did with the carbonyl group. I can do the same thing with cyanide. It means I can, add something to the molecule, and that's the beauty of the cyanide, substituent. The cyanide will give you more option to technically do decoration on the molecule. When I say decoration, adding different substituent to that molecule. Now, it depends what you start with. You might get, like a tertiary alcohol or like a secondary alcohol plus the cyanide group. Let's practice some example. The first one, we have a ketone. I'm going to say this one is a ketone molecule, and next one is aldehyde. And the reaction is going to happen in the presence of trace of acid. So always we have a cyanide, and cyanide as a nucleophile, and also the acidic version of it, or HCN. And we know HCN, it can react, for example, with water, and it will generate this for us, hydronium ion plus CN. Now, we are adding cyanide to the reaction. And also we have a trace of HCN there inside the solution. And so I know cyanide is going to attack the carbonyl group, and it will give me this one. And so I get O with a negative charge, and also CN. And if I add H plus, and where can I find H plus? Is something, like the acid. Acid is going to give you H plus, and that's going to turn to OH. And we get CN here, CH3, and CH3. Okay, so the carbon that I'm going to highlight, that carbon is attached to 3 carbons. Okay, so it will be a tertiary, and alcohol, it will be a tertiary alcohol. We started with a ketone, and we got a tertiary alcohol. Now, aldehyde, we have a primary carbon there. And so the primary carbon is supposed to give me a secondary alcohol. Let's see how we can get it. Again, first step, it will be similar to the ketone. We have a cyanide there. Now we have a negative charge here, plus H plus. That's going to give us a final product, which is going to be this one. OH. I got CN here, and I have hydrogen there. And let me write a different color. Hydrogen and this hydrogen. I'm gonna write it a black black color to show that came from the acidic from the acid technically. Now put a star on this carbon. That carbon, it has 4 different substituents, and so that means it's a chiral center. And the alcohol we got is going to be a secondary alcohol because the carbon I highlighted attached to carbon from cyanide and 1 carbon from the ring, so it will be a secondary alcohol. That means we have 2 enantiomers, and 1 enantiomer it will be this. I have a phenyl ring, and then let's say we have a CH3 here. What else? We have cyanide and hydrogen. Forgive me, we have cyanide, not methyl. We have cyanide, and we have OH. I'm going to show OH pointing to us. And hydrogen is back up the molecule. That's going to give us 1. We have 2, 3, and this one, it will be R. And next one is just simply change position of hydrogen with the OH, and that's going to give you that's going to give you the S configuration. So we will have H here, hydrogen, OH is going to be back of the molecule. We have cyanide there, and we have the phenyl ring here. And that's going to be 1, 2, 3, supposed to be R, but because hydrogen is facing to us, we will flip it, and this one, it will be S. So in case of aldehyde, if you add cyanide to it, for sure, you're going to get a chiral center. That means you will have an enantiomer. So when you write, when you write any of this product, you should add this word to it, En, to show that we have an enantiomer. Okay, if you draw any of this molecule, just simply add En and to say that there is another version of it. How about ketone? Can we get, chiral center if the 2 substituents attached to the carbonyl group are not identical? If your ketone is asymmetrical, in that case, yes, whenever you add cyanide to it, you will get chiral center. But if it's symmetrical, if your ketone is symmetrical, no, because the 2 substituents will be identical. I said that there's a beauty with the cyanide group because it has a pi bond. You can do something with it. You can reduce it and get other actually functional group. And so technically that triple bond, it will be placed off further chemical reaction. We can play with that one. If you add reducing agent to it, you will turn it to, you will not only extend the length of the molecule by 1 carbon atom, you will also have an amine substituent. Now we have this one. Or if you if you add it to aqueous solution and you heat it, now we will go. Technically, we get alcohol that is attached to a double bond, so we will have a ketoenol tautomerization, and that's going to turn to acid. Okay, let's practice the first one. The first one, we have a source of H or hydride. So I'm going to have a source of H minus or hydride. The hydride, it will be my nucleophile, and it will attack one of this center. I need to figure which one it will be the subject of the attack. We have nitrogen with higher electronegativity than carbon. So that means always we have some pooling effect from nitrogen, and nitrogen is going to have negative charge, and carbon it will have a positive charge. Now, if you have a nucleophile will attack carbon. But if you have H plus or anything with a positive charge, say this one is M with a positive charge, in that case, they will find the lone pair. So nucleophile will go after carbon, while electrophile will go after nitrogen because it has the lone pair on it. Okay, and in this case, we are adding H minus, and H minus, it will be the nucleophile. So this one, it will be the nucleophile, and it's gonna go after carbon. And this is gonna happen. We will have COH, and then now we will have hydride attached to it. And that's going to shift, that's going to move one of the pi bond to nitrogen. Now we will have a nitrogen that's attached to carbon. They're a double bond. Nitrogen had 1 lone pair. Now it's going to get another lone pair, and that's going to be minus. Okay. And I can, I can add H plus to it, or I can keep adding another mole of a hydride, and then at the end neutralize it. Now, if I add another, okay, so that one, let's say we added X's or 2 mole from that reducing agent. If I add another mole of H minus, this is going to happen. Again, this one is going to move there. We'll have nitrogen with 3 lone pairs. Now nitrogen is -2. and you can, add H plus to it. I can add the 2 mole H plus to it, and that's gonna turn it to such a compound. Okay, so the thing that you really need to know is like you have a triple bond. One of them is sigma, and two of them are pi bond. Okay, I have 2 pi bonds. So I need to have 2 mole from reducing agent. I'm going to add 2 H minus. Because I added 2 H minus, I will get -2 charge, -2 charge on nitrogen. I need to neutralize it with an acid, and that acid, like any source of acidic H, and it's going to be good enough to neutralize the nitrogen, and it will leave me. And it will leave me with NH2 that is on one side attached to carbon and other side to hydrogen, and there is a lone pair on it. So what did we get? We got a system that, like it has OH and then an amino group at the same time. Okay, and you might say, like, do I need to add the acid like right after, say, for example, after I got this one, do I need to add the acid? If you add acid to the system, very soon you will kill your, reducing agent. Your reducing agent is like H minus. H minus is going to react with H plus, and it will give you hydrogen gas. And this one, it will leave the system. So it's not going to be inside the solution. So we're going to keep dumping, reducing agent. Yes, the system is not going to be maybe that is stable, but because it's a strong reducing agent, it's going to force the reaction to move forward. And at the end, I'm going to quench it, or I'm going to stop the chemical reaction by adding acidic solution to it, and that's going to neutralize the compound. And if there is excess of this compound, lithium aluminum hydrogen inside the lithium aluminum hydride inside the solution, if you add the acid to it, very soon it will turn it to lithium hydroxide. Aluminum also can turn to aluminum hydroxide, and hydrogen hydride, it will react with acidic H, and it will turn to hydrogen gas. But the reaction is really severe, so you need to be careful and not like create too much heat. Otherwise, you might set that chemical lab on fire. And this is going to be the end of this lecture, and thank you very much.